Okay, good morning, everyone. In this video, we are going to learn about multi-level paging, or also known as hierarchical paging, tree-structured paging, or recursive paging. Okay, so as we have already learned in the previous video, that if we choose the size of the page table to be less or small, then the number of page table entries will be more, which increases the page table size overhead. So the objective of multi-level paging is to reduce page table size overhead. How it can reduce the page table size overhead is such that, okay, first of all, uh, there is a data which is stored in a memory, and this data has its page table also stored in a memory. So what happen is that instead of like a complete array of page table, we block this page table into multiple pages. So here it looks like this. If this assume this is the page table, so what happen is that like this page table is very huge. So what we do in multi-level paging, we divide this page table into multiple smaller page tables, okay, like this and this. So what happened is that like now this part of a page table has its like own entry system. This has own entry system, and this has its rows entry system, and this is an own entry system. So now we create another page table which refers to this page, this entry. Sorry, this refers to this entries, and this entry. Therefore, we tend to reduce page table size overhead. But what's the drawback of this? It has its drawback that it increases memory access time. So, paging as a concept involved first divide the address space into pages, then store the pages in each frame. Frame is basically physical address space, and accessing these pages through page table. So, ideally, the page table of a process should be accommodable in only one frame of a memory. If we take the ideal case, the page table should be stored in one page of a memory. So how this like level of paging happens? First, assume like there is only one page table. So what happen is like if level of paging is one, then then how this like virtual address space is divided? It divides into two things: P, which refer to the page number, and D, the offset. If the level of paging is two, like there are two page table, P1 and P2, then how this thing divides? So basically, P divide into two part, P1 and P2. Similarly, if we want to divide further, we just go on like now P1 divided into two parts, P3, P4. Similarly, P3 divides. So this keeps on going and happening. So the level of paging, what happens is that it reduces the page table size overhead, and but it increases the memory access time for each level of access. See, a page table is stored in a memory. So like if there are two level of paging, so first of all you want to access the memory block. To access the address of the memory block, we require two memory access plus one access for the data to bought from memory to cache memory or the CPU. So therefore, we increases the number of time memory is accessed, which increases nothing but memory access time. So it impacts memory access time. So how we can like reduce it? By using TLB. TLB refers to translation look aside buffer, or physical address cache. Memory access time is m. Memory access time is n, and effective memory access time with two level paging is now 3m. How 3m? Two for page table access and one for accessing the data. So what happen if there is n level page tabling, then memory access time will be n plus 1 m. To reduce this, we use technique called TLB and physical address cache. Okay, so a CPU generates like a physical, sorry, like a CPU generates logical address or a virtual address which contain page number and offset. First of all, it's then this number is passed to a TLB, which is stored in a cache translation lookup buffer, and is like the speed of this memory is comparable to is stored in a cache, or so the speed of TLB is that of a cache memory. So if it is found in TLB, if it is TLB, it means it is found. If the that page is found in a TLB, then TLB has two choice. First of all, that TLB can directly look for, as we have seen, the two options, physical address cache. Then TLB can access the request for physical address cache. If it is available in physical address cache, then it will take like minimum amount of time to access a page. If it is not available in physical address cache, then a TLB would need to access the memory. Okay. If there is a TLB miss, then we need to look for through page table. And then through page table, we will find the frame number, and that frame number is used to access the effective memory access time. Okay. So like here is the equation. X1 is the X1 is the hit ratio for TLB. X1 is the TLB hit ratio, and 1 minus X1 is the TLB miss ratio. Okay. So if there is a TLB hit, then we take the time C1 of accessing the TLB, which is C1, and X2. X2 basically, if it is found in physical, PAC hit, like physical address cache hit. If it is found in physical address cache, then there is that percentage or that ratio is X2. So if it is found in cache, therefore it is X2 C2. And if it is not found in a cache, then the time to look will be that of a memory. So if it is not found in a cache, means not found in a cache, how we can be sure like certain data is not found in a cache? We can be only be sure certain data is not in a cache after we look in the cache. So if whenever there is a cache miss, we need the time will always be C2 plus M. Why C2 plus M? Because we have to look into the cache to know that it is not present in a cache. Therefore, the C2 will always be an overhead, while if there is a like PAC miss, and if there is a TLB miss, so how we similarly if there is a TLB miss, how can we sure? First we have to look into the TLB. Therefore C1 plus twice of M, for uh, twice of M, because of two level page table. So that now to access the two level page table, we have 2M of that access type. If and after that 2M we get the frame number. So how we can we bring data so there are still two ways to bring data, either through PAC, like the physical address cache, and the second is through memory. So therefore this become the effective access memory time using TLB and physical address cache for two level page table. And size of outer page table can also be given using this formula, 2 raised to the power s minus nx plus nc. What is s? S is the total address space. Nx, so n is the okay, what's n here? Okay, I don't know what's n here. Okay, n is the number of n is the level of page table, and x is the uh, uh like um size of page table, and I hope that C refers to, okay, so X refers to page size. I hope, I'm not sure, you can just skip this part. Yeah, but you just tend not to use this formula, just do the hardcore way. And another option to reduce page table size is inverted paging. So what happened, in normal paging? So what happened in normal paging is that very simple. CPU generates the logical address. That logical address matches with the page table. So in normal page table, there is the frame number and there is the page number. Page number is acts as an index and frame number is the data in the page table. So in inverted paging, this table got reversed. Inside it stores the page number, and outside there is a frame number. So whenever CPU generates this address, we search by context. Through search by context, the searching time will be of O of n, because we need to search through every entry to find that of P. Unlike the indexing where P is the index, so we can directly access that index. In this, we have to search by context. So like we have to search each and every entries to find that of a P. And therefore, it increases memory access time, or basically the searching time for the page table. If we found that entry, then we can just look for the page table. Like we can okay, if we found the context, then we can look the index of that context, which is the frame number, and that frame number can be used to access the memory. And each frame table here, like the index is the frame, so here we call this a frame table, and each frame table contains and special index which refers to process ID, which means which process is trying to access the page table, and there is only one global page table is required in this case. Why only one global page table is required? Cause, okay, so the index is the frame. First of all, we need to know that index is the frame, and frame size is limited by the size of the memory. So if the frame is limited by the size of the memory, then it is always good to use only one page table, cause basically in this we are mapping the main memory to a virtual memory, unlike the normal paging in which we map the virtual memory to the physical memory. So if the size of the physical memory is very limited, it is better to store the whole index in the one global table. To store this, if we store this in the one global table, we require an extra like a column or a schema to store the process ID. Okay. Okay, now we are gonna study or learn about segmentation. So, why we need segmentation? So, what the problem with the paging technique is that paging does not preserves the users or programmers view of memory allocation. So, how the segmentation guarantees that? First of all, it divides the user program into multiple segments, and each segments have may have different size, and segments are stored in a physical address space, just like variable partitioning. Okay, so like you created a program which has like a five files. So what does segmentation do? So what does segmentation do? Segmentation what segmentation does, like, okay, what does segmentation do? Segmentation basically create segment for each of those five files. Okay, so now each of these five files can be of different size. Therefore, the segment table which is generated by all these five files can be of different size. So what happens is that whenever and these segments are basically sorry, you have five files, and each files is treated as one segment, and each segment has its own segment table. So now like while you running the program, um, it requires only three segments. So only these three segments can be present in a memory, or all can be present in a memory. So how are these segments present in a memory? These segments are present in a memory just like as a separate uh, identity. Okay, separate identity. So like how is this a separate identity? Like just like in the variable partitioning, if there is a process that requires uh, um a certain space in the memory, so only that space is allocated to the process. Space is allocated to the process. So just like in the segmentation, only that size of the segment is uh, only the size of the segment is allocated to the process, which does not lead to internal fragmentation. So in paging, okay, so the one thing that left is in the paging is that while we do paging, on the very last page, there may be a chance of internal fragmentation, because each page is of same size. Like if that page if that page is of a size, for example, like 200 KB, and only 1 KB of data is stored in that last page, so therefore 199 KB uh, of data is of the space is totally wasted in paging. But in segmentation, each segment can be of like 10, 20, and 40 kilobytes, and only that space is allocated to allocated in the memory, so there can be no internal fragmentation. So how segmentation works? So segment table looks like this. There is a limit and there is a base. So how does this work? Like if there is certain process which is working on this segment table, so this base will work as like that process. Like example that this is P1. So where it can access the data from 1400 to 2399, which includes 1000 bytes or whatever the size. So for 1400 plus, we can add 1000 minus 1. So this is the limit. So limit minus 1 is the range where we can access the data. So how this works? CPU generates just like a virtual address, but in this virtual address, it contains what D as an offset, and S is like uh, mm, a segment number. So what we do is in the segment number. We look for the segment number and gives the address of limit and base. And then this is passed to a trap instruction. So what is a trap? If like the offset given by the CPU is exceeds the limit. Exceeds the limit is like, okay, segment is like given like, okay, so the segment given is like for this 300 process, and the offset is of like 410. So when the 600 16 the limit of 16 sorry, the limit of 400 is passed through this. So what happened? Limit is of 400, but that offset data account for is like 410, 410, and this is like 400. Therefore it issues a trap instruction, and that query is invalidated. If the offset is within the limit, then that query or that allocation is passed through the physical memory. And now the process is works just like in a case that of a paging. So performance of paging, we have there is a temporal issue with related to time. Mean memory access time, we assume m, that therefore in normal case the effective memory access time is 2m. 1m for looking page table, and second m to access the data in the page table. Sorry, access the data in the main memory. Page table, this is page table, and this is data in main memory, and both are stored in main memory. Therefore, effective memory access time is 2m. To reduce this, we use TLP and PAC. PAC is physical address cache. Now there is an spatial space issue. So okay. So what happened in paging? There is an internal fragmentation. How there can be an internal fragmentation? As I have already told in the very last page, cause each page is of same size, and if last page contain only like 1 KB of data of the page size of having like 200 KB, therefore rest of 199 KB is wasted as internal fragmentation. Okay. Paging does not suffer from external fragmentation, as each page is of equal size. Therefore any process can take any any page or any number of page. Okay, segmentation never suffers from internal fragmentation, but it suffers from external fragmentation in form of PAS, like physical address space. So which can be solved using compaction and paging. Okay, how is that like? How can it suffers from internal fragmentation? Like, okay, so this is the memory. Okay, if this is allocated to P1 and this is allocated to P1, and this space is like of 20 KB, and this space is like of 10 KB. If another process want to come with of 30 KB size, it will not be or a process, basically segment, not process here. Uh, what happen is that this 30 KB, this 30 KB is not, cannot be allocated onto this. So what happen is that there is an external fragmentation. Okay. Now segment table size. To reduce the segment table size, we can apply paging, which is known as segmented paging. Means to overcome external fragmentation, or known as segmented paging. Okay, first is paging on segments to overcome external fragmentation, and paging on segment table when it become large.